I'm a rising senior at Brown, and I'm working here under Priyanka Chakraborty, working on quantifying the impact of atomic uncertainties on X-ray spectra.
Hi everyone, I'm Mackenzie Ferrari. I'm a rising senior at UMass Dartmouth. Here I'm working with Nancy Evans, matching the temperatures of detached eclipse and binaries.
And I have the honor of introducing the sixth colloquium speaker. We have Flora Broekgaarden, who is an almost fourth-year PhD candidate here at the CFI. Before arriving here, she studied at the University of Amsterdam for a double bachelor's degree in math and physics and astronomy. She then remained at the University of Amsterdam for another year to complete her master's. Her research interests focus on gravitational waves, massive stars, and astrophysics. She has spent some time pursuing various research projects in Washington, D.C., Copenhagen, and Edinburgh before pursuing her PhD here at Harvard. Outside of research, she participates in a lot of educational outreach and support for early career astronomers, as well as being an avid fan of running, volleyball, board games, and juggling. Please welcome our speaker, Flora. Thank you so much. And also, please make sure you have papers to vote with.
Yeah, so I hope everyone, I see that the microphone. I hope everyone, it has like, you should have 4 little sheets with colors. There's more in the back if you need some, and there's like some on the chairs if you're missing, but essential part of the presentation. I also like to say, to start with like, you know that you don't do research by yourself, and in my case, I have the very privileged situation that I get to work with a lot of awesome students, including some that are here, like Adam and Miranda, looking there on the left, who might be embarrassed, but I'm very proud of everyone, so yeah. And then I wanted to start saying like this is going to be, as maybe you saw, a flip talk, which means it's going to be a little bit interactive, and for that you need those 4 sheets, and I'll be asking like some questions that you can like vote on, because I like to get some of the audience opinions. And so to just start to see if it works, let's practice. So I put 2 quotes, which are, "We are all made of star stuff," and "Not only do we live among stars, the stars live within us." And my question to you is, do these quotes sound familiar? So put your white thing if you say like, yes, I even have like some shirt or some cool book with on them. Yellow, I know these. Some sound somewhat familiar, and never in my life heard of this, but I'm happy you're putting them here on. So see a lot of yellow. Can someone tell me from whom these are? Yeah, Carl Sagan is one. Other famous astronomer that comes to mind?
Dr. Tyson.
Yeah.
Okay.
So it's from Carl Sagan and Neil deGrasse Tyson. And if anything, today I want to leave you with my own inspiring quote next to it, which is, "Cabbages can be excellent stars." Star quote. And I'll show you why this is the case, if anything. Okay, so but before that, let's talk about black holes, and especially gravitational waves. But in order to go there, we kind of have to start a little bit with what are black holes. And I think it's extremely exciting right now to think about black holes, and especially stellar mass black holes, because we are, at this point right now, at what I would call the tipping point, where we're going from a few hundreds of observations of these sources to like many hundreds of thousands of observations per year. And I think that's pretty exceptional for astronomy. But okay, what are stellar mass black holes? So a very quick introduction. If you start with a small sun-like star, so for instance, say this cabbage is a star, it will at the end of its life, so also for the sun, become like a bigger red giant when it runs out of hydrogen. And then eventually at the far end of its life, it will usually kind of like implode, shed its envelope, and become this white dwarf. So our sun will become a white dwarf. On the other hand, if you start with a somewhat bigger star, say about 10 times or 20 times the size or mass of our sun, then something similar happens. It becomes even bigger, so maybe 1,000 times its original size. And in the end, it explodes in a so-called supernova and leaves behind a black hole, which is very tiny. And so if you were to ask me, what is a stellar mass black hole? I would say stellar mass black holes form when these massive stars die. They are extremely compact objects from which no light can escape. And they form in these like energetic explosions called supernovae, although there's lots of theories that say maybe not. Yeah. And then what's interesting to maybe know is that there's a lot of stars in our Milky Way. So there's about 10 to the 11 or 100,000 million stars in our Milky Way. But I just told you that, some of these stars, they might be massive enough, they might form these black holes. So my question to you is, okay, out of those 10 to the 11 stars in our Milky Way, how many black holes, stellar mass black holes, do you think there are? So I have some options. 0, maybe there's none. About 10 or 100, so a few tens. Maybe about 10,000-ish, or maybe like hundreds of millions. See a lot of blue, some white. I'm not going to judge you if you have it wrong, by the way. I'll promise not to tell anyone. So see actually a lot of colors, and the correct, or like what we think is the answer, is about 100 million. And one way to like think about this or calculate this is that we have this like so-called initial mass function that tells you what is the probability. If you like just pick 100 stars in the Milky Way, what's the probability of the star having a certain mass? And it turns out that these more massive stars here that we think form black holes, so that are about like 20 times or up to 100 times the mass of the sun, we think they're very rare. So this is in log scale on the y-axis. So this is about 1% of all the other stars. So, if you multiply 10 to the 11 by about 1%, you get this 100 million. Fun fact, it's about the same number of kangaroos in the world, which I guess is like a nice way to either remember how many kangaroos there are or how many binary black holes. Yeah. And so one way to study these stellar mass black holes and how to find them, since they're black and no light escapes, is using X-rays. So typically what people have done is when these black holes accrete material from a companion, so here on the left in the video you see the companion star, here's the black hole, and it's accreting material in this disk. And this material can like light up as it's being accreted and basically be sent away, be emitted towards Earth, and we can detect this mostly with X-ray telescopes. And so in 1971, we discovered the first stellar mass black hole through this method, which is called Cygnus X1. But 1971, it's quite a long time ago, about 50 or even more, 50 years. And so, in that time, we have searched for a lot of these stellar mass black holes. So I guess another question I can ask, out of those, 100 millions of black holes that are in our Milky Way, how many of these stellar mass black holes do you think we have kind of detected since the first discovery in 1971? So is that 0? Well, okay, I told you we have 1, but maybe 0 more. A few tens or 100, 10 to the 4 again, or almost all, basically. See a lot of yellow, some blue. Maybe you paid attention. So it's about 10 or 100. There's about 20 that we know the masses well enough of that we can kind of study their properties. But it's not that many, right? It's like quite a little. And so this makes it very challenging for us if we really want to study the population of black holes and what they look like, what their properties are, what type of black holes can exist. And 20 is very little. To make the analogy, if, compared to like the 50 million kangaroos out there, it would be as if you go to one zoo, look at 20 kangaroos, and from that try to like understand the entire diversity of the entire population, which you can probably see that would be probably very biased to that particular zoo. But some of you might have seen that I put the funny number here. So this number says 2015. So what happened in 2015? Richard, LIGO. So in 2015, this happened, and I hope the audio didn't work.
Ladies and gentlemen, we have detected gravitational waves. We did it.
A lot of applause.
I am so pleased to be able to tell.
And so in comparison, it kind of like, for scientists, this kind of felt as like, yes, we can detect these like gravitational waves. We did it. This was like extremely exciting, right? Like by now you're probably already bored of hearing about these sources, but at the time it was like a enormous discovery. And so what did they see? Well, here's like a little bit of an animation of what we think we saw. So it's a bit hard to see because it's dark. But basically here are two black holes that are orbiting around each other. And as they're doing that and getting closer and closer, they get closer as a result from emitting these gravitational waves. And these gravitational waves are ripples in space-time itself that travel with the speed of light through our universe until they eventually reach our Earth. And as they reach the Earth, which you'll see here, they literally like squeeze and stretch space and squeeze and stretch the Earth, so even I would be like squeezed and stretched. And this is going to be a little bit exaggerated for what it looks like. It's not like this. It's very tiny. That doesn't actually happen. But we can measure this with these gravitational wave detectors that are consisting of these lasers that try to like actually detect these tiny little wiggles in space. But then not on this scale, but the scale is kind of 10 to the minus 23 centimeters or meters, so very small. And the signal looks something like this. So what the detectors actually detect is what we call the chirp. So this is the chirp from the first binary black holes. And basically, as it is merging, it kind of increases in frequency. So if you were to give sound of this, it sounds like whoop as it goes up in frequency, and the signal becomes louder and louder. And so this is what they detected. And from these, you can like match the signal and find out like what are the masses of these systems, when did they merge, and these type of properties. And this, in case you hadn't noticed, also got them the Nobel Prize in 2017 in physics to these three people that were important for making LEGO happen. And since then, there has been more detections by LEGO. So here's an example of, now they have about 100 of these sources of binary black holes, but also there's like a binary neutron star source and black hole neutron star sources that they have detected. And so you can already see there's like a lot of diversity in masses, in combinations of masses that we hope to study. And so this is very exciting. And so hopefully to go back to this point that I started with, this is exciting because this means this has just happened in the past 5 years. We already have hundreds of detections. And so we're really on this tipping point from going to these 20 detections that we had over the past 50 years to these like many hundreds of thousands of detections that we'll observe as LIGO and other detectors continue. And so this is where we are today in 2022. So we have about 100 detections. But then actually, as the years go up, we're building newer and better detectors that are here indicated with this A+, A++. And especially here, these like next generation detectors, the Cosmic Explorer and Einstein telescope, they'll really revolutionize this field and detect hundreds of thousands, if not millions of these sources per year for many years. So extremely exciting. And if that, just a number doesn't overwhelm you yet, the other exciting thing is that these sources, they also trace our universe and the cosmology of our universe, because although we're detecting them today, the sources, so for instance, the black hole pairs that formed them, might have formed early in the universe and then have in spiral time, so the time it takes to get closer and closer can take up many million years to many giga years, so many billion years. And so the things that we're seeing today with these detectors, they might actually have formed as pairs of black holes or black hole neutron stars and pairs of neutron stars much earlier in the universe. So already with detectors today, we can kind of probe the deep universe in gravitational waves. And the cool thing is that with these next generation detectors, they actually allow us to even look much deeper. And so we'll really be able to explore what these merger sources look like as a function of age in the universe and really understand what are their properties as you go up in time. At the same time, this also leads us to two of the biggest open questions, I think, in astronomy today, which is, how do these sources form? So where did they originally come from? How were they made? How did these black holes come together? And maybe most importantly, what can we actually learn about stars and our universe from these gravitational wave detections? And that's something that we sometimes call like gravitational wave paleontology. So similar to like how you use fossils to study the formation, lives, and deaths of like dinosaurs, we're trying to use stellar remnants, so these black holes, stellar mass black holes, to understand the formation, lives, and deaths of these stars. Just take a sip of water. Okay, so how do we do that? Well, maybe you would say this is simple. You just told me earlier on that these stellar mass black holes, they form from massive stars. So why don't we just start with like 2 stars that are both massive? One forms a black hole, the other one forms a black hole, they collide, we're done, right? Sounds very easy. Well, this is actually very challenging to complete that picture, and that's because of something that we call the separation problem that we have to overcome. And so in order to like understand what that is, I like to use cabbages. So why cabbages? Well, they're awesome. Cabbages are awesome to use as stars because if you scale down the universe by 1 to 10 billion, so by a factor 10 to the 10, then the sun, our sun, would be about the size of a cabbage, which is very convenient. And just to give as a reference, the Earth would be about like a poppy seed or a small grain of salt or so. And if we use this scale, how far away would the closest star to us be? So the closest star is Proxima Centauri. It's pretty far away. But on the same cabbage size scale, how far away would it be? Would it be a few cabbage distances, yellow? The radius of Boston, which is maybe about 10 kilometers, the distance between Boston and the West Coast, so LA, or the distance between here and the moon? What do you think? See some people looking around. Yeah, 4 light years, so you can do the quick calculation. How do you convert light, what is it, the AstroPi convert light years to cabbages? I should make this. The answer is about the distance from Boston to LA, so pretty far, right? And this is like why, for instance, our sun doesn't really interact with Proxima Centauri, or like we don't really notice it because it's just really far away compared to the size of a cabbage. But now my question is, okay, so say I take 2 massive stars, I make black holes from them, but they're about like, say, a solar mass or maybe 10 solar masses. How close do these 2 cabbages in cabbage scale need to be to merge within 14 gigayears? Where I put 14 gigayears, so about 10 to the 10 years, because that's what we think is about the age of our universe. And that would be about the valid age that if they merge, they can merge within the age of the universe, and therefore we can see it in our like lifetime. So is that a few cabbage distances, the radius of Boston, the distance from Boston to LA, or the distance from Boston to the moon? And this will be hard if you, this might be a guess if you don't know how we know this. So it's totally okay if you don't know. I see a lot of orange, some yellow. So it's actually a few cabbage distances, very, very close. And a person who derived this was Peters in 1964, actually as his PhD thesis. So imagine that if, in order to have 2 black holes merge within our lifetime, so within the universe that we can observe it, I would have to put the black holes like this distance from each other in the same cabbage universe. So that's really close compared to, distances of stars to each other. Really close. Now, what's the problem? Like, you could say, okay, but that's fine. I just start with 2 stars that are, a few cabbages away. They form a black hole. This one forms a black hole. They're fine. They stay together, and then they can collide and merge in the edge of the universe, and we're all happy. Well, something goes wrong. And the thing that goes wrong is this. How big does this star become, like the radius extend, when it becomes this red giant? Is that a few cabbage distances, 100 to a few thousand cabbage distances, 1 million cabbage distances, or 100 million cabbage distances? See a lot of orange and blue. So it's actually really big. It's about 100 or 1,000. For these massive stars, 1,000. So imagine, right, if I start with 2 stars like this, and now imagine that one of these becomes 1,000 times its size, it would extend like beyond this room. You probably have to like walk quite 1,000 cabbages in that direction. And so what would happen is these things are pretty gaseous. Like one star would just completely engulf the other star, and they would likely merge as stars, but not as black holes. And so we're unhappy. And this is basically what comes down to this separation problem. So somehow stars don't like to be close, but in order to have things merge in the Hubble time in the age of our universe and to see them with gravitational waves, we have to get them really, really close, a few cabbage distances. And so how do you do it? Well, it means that every theorist that tries to come up with a solution to that and tries to come up with, I think, gravitational wave sources form like this, they have to somehow overcome this problem. And so there's been a couple of solutions. The first one, and maybe the most studied ones, is that they say, okay, you know what? Maybe we start with 2 stars that are really far away, and then this one can just become a red giant and form a black hole. This one can become a red giant, but then when this one becomes a red giant, it kind of engulfs the other black hole. But in this case, the engulfing actually helps to get them close. And it's this kind of like trick or phase that's called a common envelope phase, where kind of the black hole or the companion like slowly spirals in, and basically what you end up with is a much closer system. So I have a video here that shows you, so one is a star, one is a black hole, and through the interaction with the gas, it becomes much, much closer than it started with. And so you start far away, this one can just evolve, you get them close, and then this one can become a black hole, and they're happy and close together and can merge as 2 black holes. But there's also other theories. So this is something we call in the field is that we say they still come from kind of pairs or stars that are born together. Other ways to do it is, for instance, maybe having a 3rd star be there and like interact with 3 body interactions, or have like some other tricks that keep the stars actually really small. So there's this thing called chemically homogeneous evolution, that stars can rotate very rapidly, and as a result, the stars stay very small, and so you don't have this problem that you can just put them very close in the beginning and be happy. Then there's also this other kind of part of solutions, which are called like dynamical solutions. So in this case, what you do is you kind of want to end up with a lot of black holes that are very, very packed together in these like globular clusters or young open star clusters. And there they can like interact in like 3 body interactions. I started juggling. And what usually happens in these interactions is that the lightest one will be kicked out. And as a result of kicking it out, the other 2 will get closer. And this is also how you can bring them closer together. Now, this was maybe not as accurate, my juggling, but there have been simulations. So here's an example of what such a cluster looks like. So you see a lot of things moving. These are all black holes in a cluster. And on the right, you'll see such a simulation. So there's 2 black holes. Another one comes in. They like dance around for a while and have some interactions. But what you'll see at the end of this simulation is that one will get kicked out, and the pair that ends will be in a smaller orbit. So they'll be closer together. These are in a smaller orbit than that it started with. And so that's a way to get these black holes close and get them merged in a Hubble time. But there's also been a lot of other more exotic channels proposed, such as maybe these black holes actually formed early on in the universe from these like primordial collapses and black holes that formed there. So there's a lot of people that study this. Now, this might be a wild guess for some, but if you were a scientist and you had to make a bet, which of these channels would you say, you can make a random guess, actually contributes to the current population of gravitational wave sources? If you had to make a bet right now, or no bet. You can also put all 4 if you prefer to not choose. Be friends with all the theorists, See some orange, some white. Leek and I like white, so Come on, Adam, you have to. Do you trust your own simulations? Adam's like, I'm not sure. No, so we don't know, right? So if you were to ask this, if you go to a gravitational wave conference and you were to ask the same question in a room full of theorists, you will find that everyone picks a different color. Everyone will pick a different number of colors, and people will fight about this. beyond the conference, like scream at each other for who is right. And you'll see a lot of papers that claim that their channel, we now know this channel does everything, but then other papers that claim the same. So, think we don't know. And so what would you do to resolve this? So, in the end, we like to find out what is the true channel, because then we can learn about the stars and the processes that produce them. And so what you do is what we compare these theories by producing kind of mock universes or mock populations of these channels, so stars or mock globular clusters, in these population synthesis simulations. So we kind of reproduce a mock universe. And then we look at the black hole mergers that are produced in that mock universe, and we compare the properties of these mergers, such as the rates and black hole masses or mass ratios, with the observations. And so ultimately, we try to find out, okay, which of these theories or mock universes represents best what we see with LIGO and Virgo. Now, if you would ask me what is one thing I need to know about this field, it's what I would say is called the uncertainty challenge, which is that ideally, we actually will use gravitational waves to learn everything about, or almost everything about massive stars, our universe, how our cosmology works, and all these things. But that maybe a lot of our models still have a lot of uncertainties in them that actually prevents us from doing this. And I think this is one of the biggest challenges that our field faces the coming 20 or 50 years that we kind of have to solve. So that's maybe good to know. Yeah, and so in order to really do this part where we try to learn about the formation, lives, and deaths of these massive stars, I personally think it's really vital to understand and quantify our models and all the uncertain things that go on in these models. And there's a lot of people here that work on that, so that's awesome. Okay, so as part 3, an interesting question is, how do we actually do this? So, you can ask someone like Adam, who's in the room, or Lieke van Son, who's in the back. They do a lot of this, and how do they actually go and make these mock populations? So there's kind of always 3 steps that you have to do take as a theorist. So, and here's somewhat of a schematic picture where I show this is the LIGO observations that we observed today. But what goes on beforehand is that, somehow in your mock universe, you have to form the stars. For instance, the stars then form this binary black hole pair. And then over these many gigayears, that spirals in, merges, and then we can observe it. So you kind of have to model this entire process. And so step 1 in that process is that you have to simulate or come up with a way to model the cosmic star formation history, what we call, or the cosmic universe, which tells you how many stars form as a function of time or age of the universe, and with what metallicity do they form. Because metallicity is a very important property for stars that determines how massive or how big they become. And so in these theories, what we often use are analytical formalisms. So you see on the left, there's a star formation rate. There's some other formalisms that are based on observations. We sometimes use cosmological simulations for this. So you might have heard of Illustris or some of these other fire simulations. And sometimes we try to directly kind of get these this function from observations, but this can be really, really difficult. Okay, so once we have our model for the universe and we know how many stars form as a function of time, we have to do a second thing. So we have to ask ourselves, okay, but which of these stars, how do they evolve, and how often do they actually form a binary black hole pair that can merge in a Hubble time and do all of this? And for that, we use something, at least the people in the room here, use something like a population synthesis code. In our case, it's COMPASS. And this code basically calculates, starting from 2 stars in a binary, how often it forms a gravitational wave source, or anything else. And so it takes into account these phases, such as stellar winds, or mass transfer between 2 stars, supernova explosions, or this common envelope evolution, to understand what exactly happens, how often it merges as stars versus how often it produces this gravitational wave source. So that's step 2. And then there's the third step where you kind of calculate this delay time, determine where they merge, and then decide and calculate, like, can we actually observe it? And so there's these 1, 2, 3 steps. But something I like to do is that this is actually a very complicated process. So something I like to do is like a little experiment. So I'm going to ask, I need about like 20 people to volunteer for me. And they can come forward, and I'll give them a little note. And we'll do like a little tiny experiment. So 20 volunteers. Who wants to be a binary star? And you can maybe distribute this. Yes. It's like maybe your only chance to be a binary system. Thank you. Perfect. Okay. I think I'll tell you how to do it. Okay. I think we're good. More. So you're all part of, say Adam or Lika is doing a simulation, right? You're all going to be one data point in their simulation. They usually work with millions, but that's a bit too much for this room. So each one of them, it's a lucky day, you're all one binary system. So you're all one pair of massive stars that was like formed together with different properties. Now on your sheet, I have given all these binary stars, so every one of you has given a formation redshift. So it says something, I'm a binary star system born at this redshift. And I'm going to ask you so that's what I did. I did step 1. I need to distribute my stars. So I already have given you my little papers. I've given you a certain redshift at which you were born. And so I'm going to ask you to like stand in front of this redshift diagram. And if you have the same redshift, try to stand in front of each other. So if I have redshift 2, I'm going to stand here. I've formed here. And then the next redshift 2 person is going to stand like in front. You're very lonely. Yeah. And if you can, please hold your note like in front of you, so that people in the audience can like read the number. Okay. Are there any? Do you see anything that's noticeable about how they're distributed? There's only 1 at 8, Sam. I'm sorry. Anything else? Is that? Do we expect that? Do we expect a lot of stars to be born at redshift 8? No, right? It's like kind of the early universe. Maybe not so many stars. Anything else? They like Z equals 2. Does this so if I were an astronomer and I were to think, what's the distribution of these binaries? What I would usually do is I would make a histogram. So in your case, you would have to stack each other on top of each other. And then the height of you would tell me how many are in that redshift bin. So no, I'm not going to ask you that. But if you were to do that, I think you would get a specific distribution that some of you might notice. If you want to maybe duck a little bit. If you were to do it, you would get something like this. And some people will notice as the Maddow and Fragos or Maddow and Dickinson star formation rate, which tells you how many stars are formed at each redshift. And so it peaks at 2. We think most stars were formed at redshift 2. It goes down at redshift 8. So very early on in the universe, we didn't form that many stars. And currently, today, there's also fewer stars. Okay, and there's some interesting things. You can go up. There's some interesting things. The stars that were born here, importantly, are born with much lower metallicities, so fewer metals like iron in them, compared to the stars today. And that's important for how they live their lives. Now, but this was just step 1. It's already exhausting, no? But there are 3 steps, right? So the second step that we have to do in these simulations is that I need to use Compass, my cute simulations, to calculate, okay, but which of these stars actually form a binary black hole? Because the majority doesn't, right? We saw a lot of might just, get disrupted or merge as stars. So if you flip your card, it will tell you whether you formed a binary black hole or not. And if you didn't form a binary black hole, you can go back to your seat. I'm sorry. And if you did form one, please, you can show it. And maybe flip your card so people can see your redshift. Again, so Flip it. Yeah. Is there anything that you see about which stars formed binary black holes versus not? So we see one at redshift 8.
I'd say that the stars at very low redshifts did not, probably because they didn't have the time to form black holes yet.
Yeah, that's close. So you're saying I'm observing that fewer, like there we have a much smaller efficiency or production of binary black holes compared to here. Yeah, I agree with that. Does anyone know why? So you're close, like you haven't really done the time yet. But there's something with metallicity. So this is something that we haven't told yet, but like the stars here were born with low metallicity. And so low metallicity, one of the things is that you have fewer stellar winds or less strong stellar winds. And so you actually keep most of your mass. And so it's much more likely to form a black hole than if you were born here at redshift 2 or even redshift 0. And basically, almost all stars lose so much mass that they don't form a black hole. And so they just end as like neutron stars or so. Okay, but this is 2 steps now. We need one more step, which is, this is just where you formed the bare black holes. But we want to know where do you actually merge and where can like LIGO see you. So if you look at your card, it also gives you a delay time. And this is the most challenging part for you. So the delay time is in gigayears, I think. So what you have to do is, if you're at redshift 6, you can look up on the top what gigayears you're at. And then you have to basically add a delay time. So you're adding how long it then takes you to actually merge. And you have to now go to the time where you're actually merging. So you're always moving to the left. It's just asking how much do you move to the left. Add, yeah, you're kind of adding. So if it's like 1, you add like that many gigayears. Yeah?
We were 2 and we had delay of 1. So we're Does it 1 go there?
No, sorry. I meant this. So.
How many? What was your delay time? 10. Yeah. So you started at 0.
Okay.
So you should be like here at around 9.
Delay time of 10.
Yeah. But you can sit here.
Exactly.
And then if you want, you can hold up your number again to the audience, so they can see what redshift you were formed at. So hold your number. Yeah. And hold it up. Great. Yeah. So what you can basically see is that we started with like stars being distributed at given redshifts. But then by adding these delay times, because all these stars have different delay times, some might have very long delay times, so they only merge very late. Some might be formed here and have very short delay times, so they'll basically merge directly here. And so what you're seeing is that where they actually merge is like a big distribution of where they were formed. So they were maybe formed at 6, 4, 2, but it becomes a very mixture. And so if I'm LIGO, I would be here at redshift 0. And so you guys basically don't merge at all in the current universe. I have to wait another 1 billion years. But if I'm LIGO, I'm at redshift 0, and I'm looking into the deep universe, so maybe up to redshift 1. So I would be able to see everyone who is merging in this framework. But even there, you can see, I'm seeing people from redshift 2, but also someone from redshift 8. So this is how I'm probing the very, very deep universe. But in order to do that, I have to really disentangle like where everyone was coming from to like understand it. Okay, thank you. And that disentangling, that's hard. And to give you an example of why this is hard, I want to give an example with the merger rates. So one thing that LIGO and Virgo can observe is something that we call, for instance, the binary black hole merger rate. And I'll show it here on the x-axis. And what this is showing is just the number of times 2 black holes collide in our universe per gigaparsec cubed, so that's kind of per volume, like a unit volume, per year, so per time. So how often do these black holes collide? Per volume, per time. And LIGO can observe this because they can just count the hundreds of black holes that they have detected, kind of calculate what's the volume that I looked at and how long did I look for. And from that you can derive an estimate for what we call this like local merger rate because it's close to us, so around redshift 0. And from the current estimate, like these 100 binary black holes, LIGO finds something that this rate should be somewhere between 10 and 100. And so this is the median, and then there's like some uncertainty assigned to it. And they have kind of 4 different estimates because they calculated using 4 different assumptions in this case. So okay, we know it should be somewhere between 10 and 100 from observations. But what about from these different channels? So what this video is going to show you now is these rates, but then calculated using these like mock universes from all these different theorists that came up with their own mock universe, their own theories of how these are formed. They did these simulations, these 3 steps, calculated like which ones LIGO can see, and then calculated, okay, how often does this happen? And they found this. So here, each line is one such simulation. You'll see that there's many. So here, simulations run between 1,000 and 100. Maybe the rate is between 100 and 1. And each color is a different formation channel. So one of these different ways of how you can form them. So this, for instance, globular clusters that they form dynamically. This is like nuclear star clusters. So you see again, there's like a lot of ranges and a lot of lines that sometimes span. We don't know a lot about primordial black holes. That's the thing. And we can do the same for black hole neutron stars. So we have some observations, even some knowledge from pulsars. And then there's like all these theories that can predict how often do black hole neutron stars collide. But if there's one thing, so this is like about 200 different people like sweating, putting in hours of work to like understand this rate. People like me and Lieke and Adam who would be doing these simulations. But if there's one thing that you can conclude, hopefully, from this figure, is that actually most of these theories and groups, they kind of can still somewhat match the observed rate. And moreover, maybe something that you're seeing is that, you know, when you're also laughing, is that a lot of these theories and formation channels still predict rates that span orders of magnitude. So there's a lot of uncertainty, right? So there's sometimes like 4 orders of magnitude, 2 orders here, sometimes on the upper limits. There's a lot of uncertainty here going on, like 1, 2, 3, 4, 5 orders of magnitude. It's quite a lot. And so if there's 2 conclusions, is that right now, only very few formation channels, a few of these colors, can actually be ruled out by just comparing them with observations. And secondly, these mock universes, they're very uncertain in what rates they predict. And so there's really orders of magnitudes that can come out. And so where is this uncertainty coming from? Well, it turns out that we don't really understand how stars evolve and how these stars are born. And so there's lots of uncertainty on how this common envelope phase works, how stellar winds works, also something Lieke works on a lot, how supernovae work, what the properties are at birth of these different environments, and so on and so on. And so sometimes when I look at this and think about this, I get a bit sad. And sometimes it makes me think, you know, with so many uncertainties on top of uncertainty, can we learn anything from gravitational waves about any astrophysics? And maybe that's a good point to ask you, how are you feeling? Do you think gravitational waves are doomed? Do you think you need more coffee? Are you actually excited still, or maybe even something completely else? Lieke is still excited. I see a lot of blue. Okay, we need more coffee too. I agree with that. Yeah, that's a good one. So, a good question to ask, what now? What do we do? And I'll just give you some thoughts, which I think, and show you some results from the current field. But answering this question is really something that's an open question, and we're working on right now very actively. So, one thing that I also worked on a lot is that we're trying to understand, okay, there's all these different uncertainties, but can we maybe at least try to understand how all these uncertainties like impact, for instance, this local rate? So on the y-axis, again, it's this merger rate of how often, in this case, black hole and neutron stars collide. And then on the x-axis, as you go to the right, I vary like different uncertainties or use different models for these uncertain stellar evolution phases. While kind of if you go up in these models, I use like different mock universes. And something that you see already in this plot is that the rate changes a lot. So in this case by, factor 400, and that's causing this like scatter in the rate that you saw before. But at the same time, this is the observed rate, so maybe we can already start to constrain some of these models as long as we model this enough. And you can do the same for binary black holes, which is shown here, where you actually see that the variation in this right thing that we vary is not as significant as maybe the variation in like what we assume for the universe. And you can do the same for these neutron star mergers, where again, you find a little bit different behavior as a function of these models. And that's something we can use. And this different behavior, I think, we think it's related to like how this metallicity that we spoke about impacts like how likely you are to form these systems. But that's quite a lot of detail. And so one of the things that people are thinking about is like, maybe if we really use all from information, so like we try to match both binary neutron stars, black hole neutron star mergers, and binary black holes, all of which LIGO are observing, we can actually start like constraining some of these models. However, of course, one thing that's important is like asking, well, did all these gravitational wave mergers actually form from the same formation channel, which is a requirement to do this? What do you think, yes or no? I see a lot of orange. Yeah, I probably agree that if we're lucky, then maybe yes. If we're less lucky, then no. And we first have to figure out how these formation channels contribute. Now, of course, we don't only have rates. We can also look at distribution shapes. So here are, for instance, some mass distributions of these systems. And then, which you can see changes a lot as you kind of vary the same models. And then you can use, for instance, observations. So here are, for instance, 2 observations, and maybe say, oh, maybe the models that don't really produce those observations, like this one, are less likely to be true. And then there's currently a lot of work done on trying to understand these different formation channels. So maybe different formation channels, which are the different colors here, actually have different behavior in observation. So maybe they do produce different spins or different mass ratios or different masses. That will allow us to distinguish between these channels. Other things, so something that also Lieke and Adam work a lot on is, for instance, we are now so far looking at things like what is the merger rate locally, but maybe these channels and some of the behavior is also very different when we look at a function of redshift. So if we really start looking at redshifts close to us, but also as a function of redshifts far away from us, which these, especially next generation detectors, will really start doing. So I think that's really cool. And then just to give another example for this end is we can also look at other like observational constraints. So especially when you have binary neutron star mergers or black hole neutron star mergers, they might also show up as pulsar black hole systems in our Milky Way that we might see with like SKA or radio surveys. Or there's also this other gravitational wave detector, LISA, that is planned to be a space-based gravitational wave detector that might also see these black hole neutron star, binary black hole populations like earlier on. And then the other thing is that luckily there's also a lot of theorists, also here at CFA, that hopefully will help improve of our stellar evolution models and better understand some of the astrophysics. Because right now, for instance, like most of our models really rely on this like one code that someone made 20 years ago. But there's a lot of people working on kind of making more detailed like MESA codes for like how stars evolve that will hopefully reduce some of the uncertainty. And then there's also a lot of people working on making some of these models faster and like less computationally expensive that will allow us to kind of run more of them and fully explore like the full parameter space. So I'm giving some examples here of people that have worked on it because I'm very interested in this part too. But with that, we're kind of at the end of the presentation. There's like much more to show, but I don't want to go on for another 2 hours. I want to end kind of like here, which is hopefully to get you back into some excitement, which is right now we're here at these like having a few hundred of observations. But it's super exciting that like within our academic lifetimes, which is, the coming 30 years. So, maybe by this time, some of you will be like a professor or like applying for professorships. In that timeline, we'll really go from like a few hundreds of observations to this era where we have like hundreds of thousands, if not millions, of detections per year, which I think is extremely exciting. And so although we have this problem where right now, I'm not sure if we can really learn from gravitational waves yet because of all these uncertainties, I think in the coming 30 years, or like 10, 30 years, if we really tackle, I know it's long term, if we really tackle this problem where we try to understand what is the impact of the uncertainties, how can we maybe get rid of these uncertainties, how can we truly model like all these processes, we'll actually be able to start doing this and start being more on the left of this picture where we can really truly learn from all of these sources. And so maybe as a hopeful note, I think there's a lot of work that needs to be done in the coming 30 years. So please join us in this endeavor. Both me and Lieke probably will work with a lot of students in the coming 5, 10, 20, 30 years. So if you're ever looking for a PhD in the future, or just some fun people to work with, come join us. And if you're interested in gravitational wave, we also run, Lieke and I and some other people run like a gravitational wave group that you can join, and we have some like fun meetings and discussions on this topic, including 2 people who work a lot on this visiting us next week. And with that, I'll say thank you.
We have some time for any questions, if anyone has any.
I was just wondering, what are some of the mechanisms that cause like those like spiral in time scales to be so long?
To be so long, yeah. So what are some of the mechanisms that cause these delay times to be so long? Yeah, so actually this delay time or spiral in, it kind of grows exponentially with how close you are. So this Peters formula, it tells you like, oh, if you're very far away, the only reason that makes you spiral in is the loss of gravitational waves. But if you're very far from each other, then the loss of gravitational waves is very small because it goes as a function of distance. And so you just lose a very little energy, and it will take really, really long before you're closer. And then in the end, it goes really fast, and it goes almost at the speed of light when you come closer and closer. So one of the reasons is just that, like, how long it takes to spiral in is mostly a function of, like, how close you were when you formed your 2 black holes. And it goes kind of as separation to the power 4th. So it's like, if you're 10 times closer as pairs of black holes, you spiral in 10 to the 4 times faster than when you're further away. Mm-hmm. Yeah, that's a good question. So shy.
So you talked about these second or third generation experiments, and they're going to give you much more data. Are they going to give us better spatial resolution on locations on the events?
That's a really good question, and I have a plot for that. The answer is yes and no. It also still depends a bit on how they are designed, which they're still discussing today. Let's see if... So this is, for instance, for one of those detectors on the left. You'll see like the average or median localization for these different sources. And I think on the Y, it's just kind of like they say for like the sources with the highest SNR and in degrees squared. So you'll see there's like a range of things. The nice thing is they'll actually be much longer in band. So in LIGO, these sources, we only observe them for like a few milliseconds or a few seconds. But these sources, they might be in band for like several minutes or so, just because the detectors are better and at lower frequencies. And that will actually allow you, like being in band for like a minute or so, will allow you that actually the rotation of the Earth can be used, just like VLBI can be used to actually understand where they're coming from. But then one of the problems is they're still very expensive, so you can't just like, usually it helps to build more of them, so you can kind of use the delay between 2 detectors at different places of the gravitational wave source to see where they come from. But then they're so expensive, these detectors, like a few billion, that probably won't help you as much. But then they still plan to use like each detector to build at least 2 or 3 arms, so you can still do a little bit of that. Yeah, but that will be one of the challenges. And it's one of the things that they're kind of now discussing, like how much should you optimize the localization versus other like uncertainty on the redshift or other things for the science questions you want to answer. And one of the nice things, hopefully, is at least for those binary neutron sources, if they have electromagnetic counterparts, things like Fermi or like detecting those with the electromagnetic counterparts will be much better in localizing the source compared to gravitational wave detectors. So hopefully, if there is something, we will know the location from other resources.
Could you maybe explain more, just the graphic of like all modern research in this one code from 20 years ago, and like how people are working on optimizing that, and just like how computationally expensive these models are?
Yeah, so that's a really good question. So there's basically this code, SSE and BSE code from like 2000, 2002, that almost all modern day codes like Compass that, try to determine how do you go from 2 stars to 2 black holes are based on. But this code, as you can see, is like 20 years old. It was based on So you need some tracks that tell you how does a star evolve, and it was like based on very small set of tracks for a very small range of stars. But it's kind of like a neat code because it was very computationally cheap. And so actually using this code, it takes you only like 1 second to go from pairs of stars to did it form a gravitational source. And you need that because if you think about, for instance, our Milky Way, well, say you want to get like, maybe at least like 1,000 binary black hole mergers in our simulation, in order to go there, well, black holes were already rare, like only 1% of all stars form black holes. These black hole sources are even more rare, and like only maybe 1 in a million or 100 million forms like a merger. And so you need to simulate like many millions or billions of stars to get maybe a handful of black hole systems. So your total simulation still takes a day or like several days to complete, which becomes like computationally limited. And so there's 2 ways to go. And like, people really want to go to these more detailed stellar evolution tracks that are much better tracking like how stars actually evolve and use much of our modern knowledge. So things like MESA, that some of you might heard of. But then those, each simulation, so to go from 2 stars to 2 black holes, takes like several days instead of 1 second. So then if you want to do billions of stars, you need like billions of days, which, very easily goes bad. So current codes to try to improve on this try to use like some combination of the 2. So they try to do these detailed studies that take like a day per star, but then interpolate, kind of make a guess of in-between spaces. So you don't have to do a billion, but maybe only like 1,000, and then make some good guesses. And people try to therefore like speed up some of these codes, because that, if you can save a factor 100, a day becomes like 100th of a day, which becomes more feasible. So there's a lot of effort going there too. That's a good one.
Could you explain in a little more depth the impact of metallicity on stellar winds?
Yeah, and actually, like Licker, for instance, like definitely more of an expert on that. But the classic things that people say or understand now is that if you have a star and if it's born with fewer metals or lower metallicity, so fewer iron lines, then the stellar winds will be less strong because these stellar winds are usually driven by iron lines. So it's driven by electrons that like jump up and down and then produce like a photon in this process. But in order to like jump up and down, it helps if you have a lot of lines that you can jump up and down between as an electron, because then, it's just more likely that happens, and you have like different energies that can you can do that at. And so the more metals you have in your star, the more things around with a lot of lines, and so more likely this can happen that will like drive these photon winds. And so that's like one of the reasons why stars at lower metallicity, they have less strong stellar winds. And if you have less strong stellar winds, you lose less mass or photons, less energy. And so you can kind of stay more massive as star. Yeah, and then there's other effects that these metals, they also make the star kind of like a little bit bigger often. So they're more likely to kind of interact with the companion star as stars, which is not good for us. We kind of want to keep them a little bit small. And there's like a lot of these other effects that come into play when you want to make these gravitational sources.
Thank you.
It's time for probably one more question. All right, well, let's thank our speaker again. Thank you all for joining, and there might be another colloquium soon, so stay tuned.
Thanks for coming. She's